The order of the highest derivative in this differential equation is 2, so this is a second order differential equation. The dependent variable is y, and as you can see, the derivatives of y with respect to x are not raised to any power. Neither is y itself, the dependent variable, raised to any power, or is y multiplied by its derivatives. We don't see any functions of y other than functions of x times y. That's allowed. We can multiply y or the derivatives by functions of the independent variable. It turns out here that the coefficients a, b, and c are not functions of x. Well, they're constants. We could still say they're functions of x, but we have a more special situation here where a, b, and c are just numbers. Now the right hand side is some function of x, or it could be just a constant. The homogeneous form of this differential equation is the case when the right hand side is 0. When we solve a differential equation of this form, a constant coefficient second order linear differential equation, we first solve the homogeneous form. Anyway, before we do that, let's just look at some examples of second order ordinary differential equations, and let's classify them. We can see that this one here is a second order linear differential equation with constant coefficients. A is 1, b is 4, c is 3. The right hand side is a function of x. What about this one over here? Well, we could first of all divide by x to compare it to this general form up here. We get d2y dx2 plus 2 over x times y equals 0. Well, it's linear because the dependent variable y and its derivatives dy dx, d2y dx2 are not raised to any power, and we don't have products of them, and we don't have other functions of y not involving multiplication of y by functions of x. So it's linear, but the coefficients are not constants. Now in C we have a constant coefficient differential equation. A is 1, b is 3, c is 7. The dependent variable is x, the independent variable is t. Since we have 0 on the right hand side, this is a homogeneous differential equation. And in D we have another constant coefficient homogeneous differential equation. Now, as I said before, to solve this differential equation, we have to solve the homogeneous differential equation. And the solution of the homogeneous differential equation is called a complementary function. And here it's denoted by YCF. Now, it turns out that if y1 of x and y2 of x are any two solutions of a linear homogeneous second order differential equation, then the general solution is a linear combination of those two solutions. We will see some examples about this later. If two functions are linearly independent, it means that the only linear combination of them that gives 0 occurs when the constants a and b are both 0. So in other words, one function isn't a constant multiple of the other function. So let's take this example. Here we have a constant coefficient linear homogeneous equation, and we want to verify that e to the 4x and e to the 2x satisfy it. Well, we just plug in. So let's take e to the 4x, get its derivative. Well, differentiate e to the something, we get it back, and multiply by the derivative of the power. The derivative of 4x is 4. To get a second derivative, we have 4 times the derivative of e to the 4x. That's 4 times 4e to the 4x, or 16e to the 4x. So we sub these into the differential equation. For y, of course, we sub in e to the 4x. So this is what we get. And we have 16 minus 24 plus 8. That's minus 8 plus 8, which is 0. And similarly, if we check e to the 2x, we will find that that's also a solution. Now, these two solutions of the homogeneous differential equation are linearly independent. So that means that, we can't write e to the 4x, say, as a constant k times the other function e to the 2x. And it's very easy to see that, actually, because if we try to calculate the constant, we get e to the 4x divided by e to the 2x. And that's e to the 4x minus 2x, or e to the 2x. We get e to the power of 2x, which is not constant. It's not a number. It involves x. So now we can go back here and use this previous result that we saw, that if y1 and y2 are linearly independent, then we can get a solution to the homogeneous equation by getting a linear combination of them. So here we get a linear combination of e to the 4x and e to the 2x. So a and b are arbitrary constants. Now it's very easy to see that a linear combination of these two solutions is indeed a solution of the differential equation. We just plug this into the differential equation. Let's get dy dx. So we get 4a e to the 4x plus 2b e to the 2x. That's just differentiating using the chain rule for the exponential function. And as for the second derivative, well, we just get 4a e to the 4x back. A is just a constant, but we multiply by 4 to get 16. And we just get this back, but we multiply by the derivative of 2x, which is 2. So we get 4b e to the 2x. So here's our differential equation. Let's plug these three things into it. So we're going to get all of this here for d2y dx2. Okay, so I've plugged in for the derivatives and for y as well, of course. Actually, we've 8 times y. Now I will factorize a out of this. So we have 16 e to the 4x here, and over here we have minus 24 e to the 4x, and over here we have 8 e to the 4x. But notice that this is what we get if we plug in y equals e to the 4x into this differential equation. See, if we differentiate it once, we get 4 e to the 4x times minus 6 gives us the minus 24, and we plug it in here for y, so we have 8 times it. And the second derivative will give us 4 times 4, or 16 e to the 4x. So it's like we're multiplying a by the result of plugging this function here into the differential equation. And of course, we know that e to the 4x satisfies this equation, so we know we're going to get 0. And as you see, we do get 0. So all of this is 0. We can do the same for b, of course. Take out the b, and we'll have a similar scenario here. We get 4 e to the 2x. Over here we get minus 12 e to the 2x, and here we get 8 e to the 2x. And this is what we get if we plug in e to the power of 2x into our differential equation. We know from the previous bit that e to the 2x is a solution, so this of course gives us 0. As you can see, we get minus 8 plus 8 e to the 2x, so we get 0 e to the 2x, which is 0. So we get a times 0 plus b times 0, so the whole thing is 0. So that tells us that a linear combination of these two functions is a solution of the differential equation. So it doesn't matter what a and b are, because we're multiplying a by 0, and over here we're multiplying b by 0, so we're going to get 0. So that's a proof, at least for this particular case, that a linear combination of the solutions e to the 4x and e to the 2x is another solution of the ODE. In this example, we're going to find the values of k so that y equals a to the kx is a solution of this second order homogeneous differential equation. So we have constant coefficients here. So we could call this a trial solution. See, the derivative of an exponential function is just an exponential function, so we'll just have a load of exponentials here. We will have exponentials appearing in each term actually, so we can divide across by the exponential term since we just have 0 on the right hand side. So we have to determine what k must be if e to the kx solves the equation. So we get the first derivative, well, that's just a chain rule again, k e to the kx. The second derivative is k times k, or k squared e to the kx. We substitute into the differential equation, so we have k squared e to the kx minus the first derivative, and then minus 6 times y equals 0. And as you can see, we can factorize that. We can take out e to the kx, it appears in the three terms. So that's why we choose a trial solution that has an exponential form, because it will appear in the three terms, and we can factorize it out and we can solve the resulting equation for k. So we have a product of two things giving 0. The only way that can happen is if one of these factors or both is 0. Now e to the power of kx is never 0, no matter what k is. So we must have that the quadratic expression here is 0 if we want solutions. So we solve this quadratic equation. It has factors, so putting each factor equal to 0, since we have 0 on the right hand side, we can get values of k such that y equals e to the kx is a solution of the differential equation. So when k is 3, we get e to the 3x. When k is minus 2, we get e to the minus 2x. Now these are linearly independent. There's no way you can write e to the 3x as a constant multiple of e to the minus 2x. Simply just divide one by the other and you'll have a function of x. You won't have a constant. So we know that if the solutions are linearly independent, we can get a linear combination of the solutions to create a new solution of the differential equation. Now k squared minus k minus 6 equals 0 is called the auxiliary equation, and we can get that very easily by looking at the coefficients of the constant coefficient differential equation. So it's 1k squared minus 1k minus 6 equals 0. So we just look at the coefficients that were called a, b and c at the start. So a is 1, b is minus 1, c is minus 6. Now here is another example. So you know what's going to happen. The auxiliary equation is going to be 1k squared minus 3k plus 2 equals 0. That'll be the result of substituting e to the kx in. This equation has factors. The factors of plus 2 are minus 1 by minus 2, and you'll see it will work out. So we solve to get k, so k can be 1 or k can be 2. So we have e to the 1x or e to the 2x, and then we take a linear combination of those solutions. Here's the general situation. A, b and c are constant coefficients. So if we run through what we did, we will end up getting this equation here. So we just multiply a by k squared, b by k, and then we have plus c. That gives us our auxiliary equation. And this product is 0, so the quadratic is 0. So that's the general situation there.